Okay, hello. Today we're going to look at something new called game playing. It's more to do with search again, actually, but slightly different. And we're going to look at a particular kind of game playing, which is called game playing with perfect information. So the outline is going to be, talking a bit about game playing as an adversarial search problem. It's just setting the scene and getting you to understand how game playing is done. And then we're going to look at the Minimax algorithm first, and then the alpha beta pruning, which is another algorithm. Okay, so in game playing, if you think about game playing, it's actually it is a search problem because we have seen games, right? I mean, we've seen simple games like eight puzzle, eight queens. Okay, we've seen at those kind of games where there's only a single agent trying to find like a path or a solution to very specific problem. But when you think about like a competitive environment in a game where you actually have more than one player, right? This is a competitive environment. This is kind of probably the game that you play with your friends or online and so on. You're actually not just playing by yourself unless it's like solitaire or some of those games we've seen before. Um, you actually have multiple agents, or let's say we're focusing on two agents, and the agents' goals are actually in conflict. So that means a move that someone might make in chess is supposed to hurt your opponent, right? You're not trying to help your opponent, you're trying to help yourself, but helping yourself actually hurts your opponent, right? So the goals are actually in conflict. You have one agent who's trying to, let's say, maximize their gains, and the other agent is trying to maximize their gains, or in other words trying to minimize your gains. So gives rise to these adversarial search problems, because you actually have an opponent, and that opponent has an opposing view, if you like, or has a completely different viewpoint of this game. And these kind of games where they are deterministic, okay, they are like turn taking, I do something, you do something, two player, um, zero sum, okay, we'll look at this in a while. These games are called perfect information games, okay, that means they're deterministic, fully observable, so you can actually see the state of what were the previous moves. You can see the whole state of the game. Nothing is hidden from you. That's like chess, and it's the same with Go, right? You can see the positions at the board. No one is hiding anything from you, um, and you just have to know what is the best move you're going to take right now. But you also think, okay, I may take a move. There's so many valid moves at a current position, but you also think about, well, what is my opponent going to do if I take one of these moves, right? One move might look very good at the moment, but maybe you can eat a pawn or something. But then is that then going to put you in a vulnerable position, and the opponent is then going to get a far more valuable piece from you. So this is the interesting thing about two-player games. But again, with perfect information, we're thinking about games where you both have access to the full board, okay, um, and you both have some kind of winning or losing chance. That's what games are about, um, and games are actually very hard to solve, right? They're interesting, but actually they're they're hard to solve, these kind of games that we're talking about. So chess has a branching factor of about 35, and each player will make roughly about 50 moves. So that means that like 100 moves, the depth is 100 around, okay? And that's going to be a very, very intractable problem, because that means that there are more chess moves, possible chess moves, than the number of atoms in the universe. So this is extremely impractical to implement if you want to do it in the classical search setting, right? And if you look at Go's average branching factor is 250. Okay, so that's huge. But we've seen that AlphaGo, an AI, a game playing agent, has managed to beat the best Go player in the world, who happens to be Korean, about 4 years ago. So this is very, very interesting, yeah. But obviously, it wasn't using, a very naive, search like depth first search or A star. Okay, it's a complex algorithm that doesn't use these basic things because it would become just intractable. The number of states are just way too many to keep track of, and computers don't have that kind of ability. So games are always such an interesting domain. People have done PhDs in games. People have actually um, dedicated their lives to working on games because maybe they love playing those games themselves, and therefore they end up working on them because they're very curious about how to go about working out or improving some algorithms. How do we automate, like an automated chess player or Go player that can, beat any humans? And this is the result of some of the milestones we've had in AI, with chess back in the 90s and then AlphaGo in, just 2016. So, like the real world, like the kind of problems we've seen before, games actually requires the ability to make some decision even when calculating the optimal decision isn't feasible. Because if you're going to, you know, apply like A star on playing chess, but imagine the depth is about 100, and that the branching factor is about 35, and by the time you're trying to calculate the heuristic value and the path cost, this is just way too impractical. So you have to work and make decisions when you cannot do these kind of optimal decision calculation like in pathfinding. Yeah, I mean, it is pathfinding, but it's just rather intractable at this stage. So looking at games and search, I think I've already spoken about this just now. In a normal search problem, the optimal solution would be a sequence of actions leading to a goal state, right? So you have a goal state, and you're just trying to get to this goal state. Either you are traversing, you're going through a map and cities, okay, or you're doing the eight puzzle, or you're doing the eight queens, right? But in games, you have an opponent, right? You have another agent playing, and that agent is actually almost contradictory to you, right? So this opponent can act in an unpredictable manner because you don't know what they're going to do. But one good way of thinking when you play a game, and I think most people do that, is they always think that no matter what step they take, the opponent is going to take the most optimal step for them, right? We always think in the worst case scenario, right? Whatever I do now, let's say the next player B has three options, and one of them is going to make not hurt me so much. One of them is going to make me win, and one of them is going to really hurt me a lot. You would imagine that B would take the third step, which is going to hurt you a lot, instead of the second step that's just going to make you win. But you never know, right? It's just that in these kind of strategy building and playing, you always think in the worst case scenarios. So the solution is a strategy specifying a move, for every possible opponent reply. So you kind of have to go one step at a time. So what has that opponent done? What has my opponent done? And then based on their actions, I can then, decide what I can do with the options available to me. And the other thing about games is also about time limits. Well, even though we did talk about time complexity and we did say that some of these algorithms were going to take too much time, but we didn't really go into that. But in a game playing setting, we would see that, we don't want to be spending too much time, um, like solving this, right? We kind of have to, because the opponent can't be waiting forever for you to make a move. Um, here are, just like a quick information, about some of the games that are out there. You may not know some of these games because maybe they're very old. I hope not. I know most of them. So this is the family of games we're talking about over here. Um, they are games that we are particularly interested in, that perfect information games where there's one best way to play for each player, and um, the environment is fully observable and deterministic, and you can see exactly what has happened and there's nothing hidden from you. These games may or may not be considered perfect information, even though they are here. Some people consider them as not perfect information, like uh, backgammon and Monopoly, because you have an element of chance. You have to throw the dice or something like this, so that brings in this element of chance into it. Um, and then you have games with imperfect information. So these kind of things include things like, you know, playing a game where not all the cards are available to you, like playing poker or bridge, right? So you don't know what the other person has, and maybe you have to make a decision without being able to see something, or there's some kind of secret information hidden from you. Unlike this perfect information where everything is actually out there and you can assess the situation. So we're not going to look at this, but it's just good to know. If you're interested, you can read more. I'll provide some links. Also, games like maybe rock paper scissors, right? It's a fair game. It's fair. At the same time, you're both supposed to make moves simultaneously, right? But without knowing what the other person is going to do. But it's still a fair game, so to speak. Yeah. I guess it's still under the imperfect information because you don't have full access to um, the whole space of your environment. So here's the setting, okay, for our perfect information games is we are looking at it as a two-player game, okay, and the players are called Max and Min. Okay, if you look at the words max and min, you might immediately think of words maximum and minimum, and you are right. It is about maximum and minimum. So we just call them max and min, respectively. And max actually moves first, so they will. Max will move first, and then Min will go, and then Max will go. So it's like most of the kind of games that you would expect, like tic tac toe or chess, Connect Four. Okay, at each turn you tend to make a move based on what you think the opponent will do next. Okay, this is what I've already mentioned earlier. You will always think, okay, if I take this move, what's that going to do to Min, and then Min will also think the same way, and they will take whichever move that's going to hurt you most and benefit them most as well. And at the end of the game, points are awarded to the winner and penalties are given to the loser. Okay, so um, I think it depends on the game, yeah? And we're going to look at a concept called pruning later on, which will allow us to ignore portions of the search tree that makes no difference to the final choice. And this will then allow us to, reduce the state space a lot. I'll talk about it a little bit down the line. Okay, so in order to to get further now, we can formalize this, okay? A lot of this will actually look quite familiar to you already. So to formalize the game definition, we have an initial state, which is just going to be given as 0. Okay, this is probably not an initial state because this is the game of tic-tac-toe. Initial state is probably just going to be an empty square, right? Like okay, this is probably going to be the initial state for tic-tac-toe, right? Because you imagine there's nothing on the board just yet. This is one of the states, I guess. And then you have a player, right? Because right now you actually have roles and you have multiple agents. So you have player in state S. So who is the player that has to make a move in state S? So if you look at this particular state, because this is noughts and crosses, tic-tac-toe, I guess since you see 2 X's and 1 naught, you imagine that maybe X had started and then naught went and then X. So in this case, the player who has to make a move is probably naught, okay? Like, because as you can see, it's only got 1 naught there, so it's naught's turn to play. So the player in this case is going to be the player who's playing naught, okay? Maybe they're min, okay? We'll look at that later. Actions as A, okay? So this is going to return the set of legal moves in state S. So what are the legal moves that I can do in this state right now? So let's say in this state now, naught can do many things, right? Naught can go here, okay, or naught can go here. Naught has basically 6 different options to pick from. This player has 6 different 6 different actions, right? We know all this. We know all this from the first chapter itself, the first or the search chapter itself. We know what actions mean. And then the result is actually the transition model, which defines the result of a move. So the results are basically, if I apply, if I apply naught here, then the new state is going to look like this, right? And as we see, the transition model is going to be a successor state, okay? This is the successor state of the previous state without the naught. And this state, as we know, is also a child, right? A child is a successor of a parent node by applying an applicable action. So the results are going to be all the new states that can be generated because of applying some applicable actions, and that actually basically mean all the children of this current state. And then we have the terminal test. Okay, the terminal test is just like a goal test, because in a game, the goal is actually to get to the end of the game. So at every step of the way, just like in the search, you have to do a goal test. So in game playing, you will run a terminal test. So the terminal test will return true if the game is over. And if it's not, it's just going to return false. So I think it's not that hard to imagine this terminal test kind of like analogous to the goal test you would do in your normal search algorithm. And then now you have something called the utility of the player P at state S. The utility is basically the objective function, right? You always have some kind of an objective function along the way. And this objective function is going to be a payoff function, right? What is this costing, or what is the objective function or the evaluation function for that player at that moment in time in that state? And normally the utility, when we use this function utility, actually, it means that in a game, we normally define it as the final numeric value for a game that ends in a terminal state S for a player P. So if we've come to the end of the game, and then we can see, what is that utility, what is that score for that player, for each player, for that player in that, end of it, or it's like a leaf node. We'll see this now in a demonstration. Um, so talking about outcomes or termination of games, you will have in these kind of games, in the not just perfect information, we also want them to be zero sum. So what that means is um, whatever happens in the end, the total payoff, right? Let's say if you win, you get one, right? If you lose and the other person gets zero, right? You win, you get one. They lose, you get zero. So 1 plus 0 is going to be 1. Likewise, if you lose, you get 0. The opponent wins and the opponent gets 1. So again, when you add up those two numbers, you're still going to get 1. So in a zero-sum game, the total payoff to all players is the same for every instance of the game. So in chess, the payoff is either 0 plus 1, if you lose and they win, okay, it's 1 plus 0, if you win and they lose, or half and half. That means you drew, okay, you couldn't finish the game, you both deadlocked, and so it's half and half, but half and half, which is 1 all the time. So they don't add up to 0 per se, but it's a very old term that was used for historical reasons. Maybe something like constant sum game, or it might make more sense. But that's what zero sum game mean. Okay, if you play a lot of games, I guess you might be able to see what are some of these zero sum games, and it's like you win and you get all, and you lose and you don't get anything, and if you draw, it's half and half. Okay, so here we have something called the game tree. Okay, so this is sort of again going back to search tree, right? This is like a search tree for tic-tac-toe. So this should look familiar to you. Maybe some of it is already there in the earlier chapters. What's different about the search tree? Okay, it's a search tree, but we call it a game tree. Why? Because firstly, you've got to map it to a game where you actually have different players. You actually have different player having, a different kind of strategy to play that game. So if we look at tic-tac-toe, as we said, this is the initial state with an empty grid. And the first player who's going to play is known as Max, right? Remember we said we have two players, Max and Min. Now Max is going to start playing this game, and let's say Max is going to put a cross, okay, or on the board. And because tic-tac-toe has got nine legal, squares, Max can put it in any one of these 9 squares, okay? And once Max has done this, it's Min's turn. And Min sees that, okay, here are all the different options, and I have to put a knot, okay? Or an O, or whatever you want to call it, yeah? So Min will have, out of this 9, 1 has been taken, so there are 8 squares left. So Min is going to have 8 possibilities, right? And then it's going to be Max's turn, and Max will put the X on one of the remaining 7, and so on and so forth. So for a simple game like tic-tac-toe, it basically has about 9 factorial, okay, because 9 times 8 by 7 by 6. But it actually has less than, approximately less, 9 factorial is a bit more than that, about 300,000. This is actually considered quite small. This is a very simple game, right? Because if we're talking about chess, that's like humongous. So the moves can be represented as a game tree, and the nodes are the states and the edges are the moves. So I think all of this should look quite familiar to you. The only difference is that at every step of the way, you have a different player. The players are alternating, and they're, doing different things to the board. In fact, there's a lot less than this. There's so many um, less possible games that you can play because not all games will have like 9 steps, right? Sometimes you play the game, you're not going to fill the board, right? Like in this particular game, you can see the game has ended because you know obviously Min has won, right? But you've only have 1, 2, 3, 4, 5, 6. It's you've won it in 6 steps, so the depth is only like 1, 2, 3, 4, 5, 6, right? And here, well, you're at a draw situation, but you've taken 9 steps to play the game. And here, it's also a draw, but you've only maybe finished at 7 steps. Okay, so not all games will go all the way down to 9. Although in this game it's Not's turn, but then you're already at a dead end because not to say no one is going to win, but if Not puts it there, then X can win. Oh, it's already, sorry, it's done. X has won. Sorry. So this is over, right? So you don't have to go on because X has won, and you're not using the 9 moves. So this is the game tree, okay, which should be quite familiar to you by now because of all these search trees you've been looking at. And we say that both players know all about the current state of the game because you can see exactly what's happening. There's nothing to hide, and you just know it's going to be your turn, and you can make a good move. And each leaf, okay, leaf meaning you're already at the end of the game, it's going to represent a win for one player, okay? Or it's going to be a draw. So these two are like wins, okay? Because this is a win for Min and this is a win for Max, and this is a draw. So you can see the utility is going to be, if Max is 1, then this is going to be 1 and 0 for Min. Okay, and here is going to be half and half, and this is going to be 0 for Max and 1 for Min. So now we're going to look at the important part of this lecture, which is the Minimax algorithm. So we want to talk about, how do we find the best moves. How does a player know what is the best move to take at a particular point in game? So we're going to do this using a very simple 2-ply game, meaning you only have 1 step, okay? It only has 2 moves in the game. 1 move by Max, followed by 1 move by Min, and that's it, and then it's game over. So it's very simple, but we need to use this simple scenario because it will help you, understand how this actually works, and then you can just apply it to more complicated games. And that's how things are normally done in computing, right? Everything is, you try to map it and show it works on a small safe scenario, and then if the problem gets really big, you just apply it because it's just computation. So just 2 moves. And if you look at this, okay, so this is a kind of convention you have to get used to. So you have Max, who is represented by a triangle or like an upward facing triangle, because Max is always trying to maximize. And in this case, you can see that Max has 3 different possibilities. Max can take 3 moves, A1, A2, or A3, right? So this is the beginning of the game. And then Min can take, these moves after Max has made A1, and then Min, who is, represented by the downward arrow because Min is always trying to minimize, Max's moves, will have these possibilities. So given a game tree, the optimal strategy can be determined from the minimax value of each node. And the minimax, which is the utility for Max being in the corresponding state, assumes that both players will play optimally. Okay, so because this is in a hypothetical situation, your strategy always has to take into account that your opponent is going to play in the most optimal way. And for a terminal state, so this is the state where the game ends, because as we said, it's only a step taken by by Max, and then a step taken by Min, and then it's done. So the game is over here. And for all these different combination of moves, you're going to get the utility value for Max. Okay, so Max will see these utility values, and then because it can see these utility values, it will try to decide what is the best thing for it to do. So Max will always prefer to move to a state of maximum value, and Min will always prefer to go to states with a minimum value, okay, because they have opposite interests. So in this scenario, let's see, okay, for this ply game, what is the best move for Max and what is the best move for Min after Max's value? So think about it this way. Max will look at all of these things and see that the worst that it, the best that it can get out of the worst is, you know, because Min is always going to take the smallest, the move with the smallest step. So you're assuming Max is going to assume that, okay, Min is going to take the 3 here, okay, because Min is always going to take the smallest move. And over here in this particular example, Min is going to take a 2. And in this particular example here, also Min will take a 2. So Max will need to see, okay, so the worst thing that can happen to me is it's going to be 2 here, it's going to be 2 here, and it's going to be 3 here. So the best thing for me to do would be to take the 3, okay, to think that I can go down the 3 here. And that's kind of how Max gets the A. And Min will also think the same way, right? Min will say, okay, Max will take, the best out of these 3 things, and so I'm going to take, the minimum out of that. So we need to find a way to represent this in an algorithmic manner, okay? We need to build an algorithm to build this. So we can say the best move for Max to take would be to take A1, okay? Because Max knows that among all these, 3 is the best out of the worst of all the possible outcomes. And because if it takes this, then, B will take the 3 and it will get a 3, right? If it takes this move, then B will take a 2, right? Min will take a 2. And if it makes this move, Min will take D3, right? So assuming Max has taken the 3, okay, taken A1, because A1 will lead to 3, then Min is going to take, B1 over here, okay? So it's going to be A1 for Max and B1 for Min for this game to be optimal for each of them. But let's see, how do we work on this in an algorithmic sense, okay? So here is the pseudocode. This is probably the most important slide of this lecture, and also the most important part that you need to focus on. So the Minimax algorithm, okay, has this pseudocode. Well, it's got this pseudocode, but let's work with this, okay? So pay attention now. So what Minimax is going to do is for a particular state it's in, it's going to do one of three things. Okay, it's going to test first, is that state a terminal state? If it's a terminal state, I'm going to return just the utility value. So basically, if it's one of these, because they will just have a utility value, and you just return that value. Say, okay, I'm finishing this game here, and the result of this game is it's going to give max 3. However, what about these other states that are not, leaf nodes? For those states, it's going to check, is the current, for that state, is the player at that state max? Okay, if it's max, then max is going to get the maximum, okay, over all the actions, okay, all the actions of its children, basically. Okay, but the children, it doesn't have immediate access to the children. The children themselves will have to run and the minimax on their children. And the children of A happens to be min, okay, all nodes belonging to min. So if the player at that particular location is min, then min is going to take the minimum of all the results of the actions applied from that node. Let's see how this works. Okay, so we start at A. Okay, A is max, so you're going to test. Is it a terminal state? No. Is the player max? Yes. So if it's going to be max, then what is it going to do? It's going to take the maximum of the function minimax, okay, just remember it's a function minimax, of its children, okay, because the result of applying actions to a state is just the children. So I'm going to have to get the result of my children, and from that result, I'm going to get the maximum. And that's, I'm done. Then I'm going to know. Okay, so it goes to the first child. Let's just say it starts here. And it's going to do this test again. Is it a terminal test? A terminal node? No. Is it max? No, because it's min. Is it min? Yes. So if it's min, what you're going to do is you're going to get the minimum. Okay, I'm going to get a minimum value of the results of applying all the possible actions from here, from state B. And therefore, I'm going to get the minimax of all my children. So therefore, I'm going to go now down to my child. So go to my first child, I go here, and this node doesn't have a name here, but you're going to do the test again. Is it a terminal test? Oh, yes, it is. So if it's a terminal test, then just return the utility value for that. And the utility value here is just 3. Okay, so return the utility, and it goes back up here, and 3 is now available. But you're not done because B has more children. So B is going to now go to the next child, which is here, by applying action B2. And you're going to check that this is a terminal test, okay? And it says, yes, this is a leaf node. So you can just return the utility. And that returns 12. And now you have 12 back here. But then you're not done because B has another child, which is over here. So it's going to go down there, and it's going to check for that node, whether it's a terminal node, a player, max, or min. It turns out it's a terminal node. So it's just going to return the utility value, which is 8. So 8 goes back up, and you're done because you have no more children. And now you have all the values returned by the children. And you can run the min function, and you see, oh, the minimum of 3, 12, and 8 is in fact 3. And B is going to propagate that value back up to A. And now A has the result of its first child, which is 3. But it's not done yet because it has 2 more children. So it goes to the second child, C, and again, it applies. It's going to do all this test again, and it's going to see that this is now a min player. So it's going to call minimum of the minimax of the C's nodes, children rather, okay? So it goes to the first child and it sees that it's a terminal node and it returns a utility value, which is 2. So 2 is brought back up and passed into that function. But that function is not complete because there's still more children. So it goes down to the second child and it sees that it's a terminal node. For a terminal node, you just return the utility function, the utility value, and now you got the utility value 4. And finally, it will go to the last node of node C, the last child of node C, and sees that it's a terminal node, and it will return the utility value for it, which is 6. So now, since C has no more children, it can evaluate the min function of its minimax, and the minimum of 2, 4, and 6 is 2. So it can now propagate that result back to A, and A gets the second value. But A is not done because it still has one last child. So this process repeats, okay? So you go to node D, you realize it's min. So because it's min, you call the minimum, you want to get the minimum of running Minimax on all its children. You go to the first child, it happens to be a terminal node, so you return the utility of that, which is 14. 14 is brought back up, and you have 14. And then you go to the next child, which is this node down here with the utility value 5. It's a terminal node, so it returns the utility value, and 5 is then there. And finally, the final child of D is by applying action D3, and it happens to be a terminal node. So you run the utility, you just return the utility, which is 2, and you're done because you've no more children. And now you can get the minimum of all these children, which is 2. And now you return 2 up, and A finally has 2. And now A is done in terms of children. It has no more children. And now it can run the maximum function over all these values. And the maximum of that is 3. So this is how the Minimax function works. And what is interesting about this is it is actually a recursive function, okay? I guess some of you are familiar with this term, okay? A recursive function is a function that calls itself back, because if you see, here you have Minimax children, and then this is one of the child, and then again it's calling Minimax. So within a call of your function, you are calling, yourself back. And recursive functions, within the recursive function, you will have a recursive case, okay? So for in this case, this is the recursive case because it's Minimax X S, and inside here you are calling Minimax again. So this is the recursive part, the self-calling part. And except that in this case, you're going to get the maximum of, the result of your Minimax. And for the minimum player, you're going to get the minimum of the result of the minimum player. But if you think about this, if you keep having this function calling itself, you might get stuck in an infinite loop. So there must be, for every recursive function, there must be a base case, okay? A base case is also called a trivial case. So in which case you have reached a very basic level in your function, and you can terminate. You can terminate because you're just going to basically return a value. So the base case actually applies to all these leaf nodes because they're already terminal nodes. You cannot further branch them out. So, and they already have utility values attached to them. So they are the base case because when you get to these leaf nodes, you can just return the utility values. And when you return the utility values, then these recursive functions will start getting partial results coming in. And when you start getting partial results, and then you can finally compute your result, and then you propagate it up again, as you saw just now. So this is the neat thing about recursive functions, right? I assume some of you already know about this, but if you don't, now would be a good time to understand this and to, to actually get it, okay? So that is your minimax function. Now, what is another observation that you might have found is the way this whole search tree or game tree was traversed. Okay, this search tree, if you saw, went down here and here, and then here and here, and went back up and went here and here and here and here, and then went here and here and here. So this is a depth-first traversal. Okay, so the properties of Minimax is it follows a depth-first traversal. Okay, with the branching factor b and depth m as before. So is this complete? Yes, it is if the tree is finite. Okay, and is it optimal? It is optimal against an optimal opponent. Okay, optimal opponent meaning the opponent is going to take the best step for them. And the time complexity is the same as your DFS, which is b to the m. And the space complexity is linear, right, which is a good thing. However, if you think about the time cost, which is exponential in the depth, it's actually not practical for real games. So, for chess, which has like, about 100 moves, 50 moves each for each player, and that's, basically the depth of 100, and branching factor of roughly around 35, you're going to have 35 to the power of 100 for the time, which is so impractical. So this brings us to, the problem that the number of game states it has to examine is exponential in the depth of the tree. So can we actually ignore some of these nodes, right? Because if we have to traverse through the whole tree, but maybe going to some of these nodes are like dead ends, like, if you go to that node, you're not going to, there's no point in going to some nodes, right? Because it's never going to give you a good outcome anyway. So this is where we want to start doing some kind of pruning. So pruning is where we can eliminate large parts of the tree, by just ignoring them. Okay, meaning we just don't even go to certain parts of the tree, and then that saves you a lot of time and also space. So pruning eliminates some possibilities from consideration, okay, without even having to examine them. So we don't even have to go there, right? That means we don't have to do all this extra work. And it allows us to ignore portions of the search tree here's the keyword, it's going to make no difference to the final choice. Okay, so we can safely ignore portions of the tree and still get the best optimal outcome for our strategy. So we're going to look at that next in the alpha beta pruning lecture.